Are you able to see my PPT?
Yes, sir.
My audio is clear, na?
Yes, sir, it's clear.
So, as we have seen, what we were dealing with, we have dealt with a shell balance for momentum transfer initially, shell balance for heat transfer, and shell balance for now we will be dealing with shell balance for mass transfer. So this is logically similar as initially we have developed a logic that heat transfer, mass transfer, and momentum transfer shares some similarities and differences. So based on that similarities, so we are studying all these transport phenomena subject. And on same line, we have discussed shell balance for momentum transfer and then shell balance for heat transfer. So what was the important parameters which we were deriving in shell balance for momentum transfer? Profile equation. Yeah, roll number 71, Himani. Yeah.
Sir,
So shell balance for momentum transfer. What was the most important profile equation we will get from that?
sir, a velocity profile equation and
Very good.
flux.
Most importantly, velocity profile equation. Once you have velocity profile equation, you can get the flux profile equation also. Similarly, in heat transfer, roll number 72, Mitali. Mitali,
Yes, sir.
what was the most important equation we will get after performing shell balance for heat transfer?
Sir, you would get temperature and the heat flux profile.
Very good. Temperature profile. Most importantly, temperature profile. Once we have temperature profile, so you can get a flux profile also, heat flux profile. So Nidhi, roll number 73, Nidhi. What is expected in shell balance for mass transfer? Outcome of this shell balance for mass transfer? Nidhi,
Yes,
for
sir.
73.
It's a Fick's law.
Yeah, equation of
Fick's law of diffusion.
Fick's law. Fick's law you will get. I am asking outcome. Outcome from momentum balance is velocity profile. Heat transfer
Concentration
is
profile.
concentration profile. So here, so we are doing all this for getting the concentration profile. So once you have concentration profile, so it is as good as you can have almost 90% of the design important parameter calculated. Once you have concentration profile in mass transfer, concentration profile means how concentration is changing with the dimensions. In my system, everywhere, what will be the concentration? That is nothing but the concentration profile. If I have that, mass transfer, almost all the problems in mass transfer will be solved, almost 90% problem. So that is what the main aim of this shell balance for mass transfer. And initially also we have discussed what is the difference between heat transfer, momentum transfer as compared to mass transfer. Most important differences. Roll number 75, Aguni.
So in mass transfer, there will be always some motion of the molecules.
Very good. Excellent. Excellent. So you can have only conductive heat transfer. Only conductive heat transfer you can have in a real life. Only conductive momentum transfer also is possible in laminar flow. But only conductive mass transfer. Conductive mass transfer means mass transfer without bulk motion is not at all possible in mass transfer. Mass transfer always associated with a bulk motion because this is the mass transfer. Molecules are moving, and certainly as soon as there is molecules are moving, bulk motion will be there. Bulk motion is associated with convection. Now, when the mass transfer is categorized into molecular transport and when mass transfer is categorized into convective transport, that depends upon a magnitude of velocity. If velocity is very large, then it will be characterized into a purely convective transport. mass transfer if velocities are larger. If velocities are smaller, magnitude of velocities are smaller, and most importantly, a mass transfer is taking place because of the concentration gradient. It is not a pressure driven flow. Velocities will be there, but it is not a pressure driven velocities. It is because of a concentration difference. Concentration difference, molecules are moving from one place to another place. That time we can categorize that kind of mass transfer into a molecular transport. Okay, so all the time, whenever there is a mass transfer, it will be associated with a convective as well as molecular transport. So all the time, whenever you are discussing shell balance for mass transfer, all the time we will be discussing combined mass flux. We will never discuss only molecular mass flux or convective mass flux. Molecular mass flux is given by fixed law of diffusion, and convective mass flux, you know, velocity is associated with this convective mass flux. So we will see that actually. So molecular mass flux is given by a fixed law of diffusion. Is already we have discussed. This is a molar molecular mass flux given by fixed law of diffusion. When total concentration of system is constant, you can write like this actually. Total concentration can be taken out. It will be dxa by dx. It is the molecular flux of component A in x direction. Similarly, it can be in mass form also. It is in molar form. C is a moles per unit volume, moles per meter cube. This is molar fraction. Similarly, I can have, this is a mass per unit volume. Density, okay? Density of compound A. If total density is constant, this will be a weight fraction. So these all are a fixed law of diffusion, and this is purely molecular transport. And as we are discussing from starting itself, mass transfer will be associated with a both modes of mass transfer will be there whenever it is there. So we will add this convective mass transfer. So this is also convective mass transfer will be associated with a velocity. Let us say v is a velocity. V is a velocity. Vx is a x component of velocity, or velocity in x direction. So Vx is a x component of velocity. So Vx into ds. ds say perpendicular surface area in x direction. So velocity in x direction multiplied by perpendicular surface area. So this will give me a volumetric flow rate. Velocity into a surface area perpendicular to flow direction, that will give me a volumetric flow rate. This will be volumetric flow rate. Now this is the mass flow rate. So this is the volumetric flow rate. This is volumetric flow rate into density. Okay, into density, this will be a mass flow rate. This is mass flow rate. Now I want mass flux divided by area. This will be a mass flowing per unit time per unit area. So this will be a mass flux in x direction. This is total mass flux in x direction. This is a velocity and x component of velocity, and this is a total density. So this will be total mass flow in x direction. This is the total mass flux in x direction. Now rho A. Now this there can be some density. Density can be you can have some additive property or some statistical equation you can arrange based on a composition. Say it consists of 10 components. Based on that, you can have this relation between an individual density and a total density. Say this is the individual density. So this will be a mass flux of component A in x direction. What is this? This will be a mass flow rate of mass flux of component A in x direction. And what is this? This is the mass flux of component A in a given direction. Okay, so this is the convective flux. Convective flux. This is in terms of mass unit when density is considered. Similarly, we can consider in terms of molar concentration. So this is the velocity. So this is the velocity in x direction. Say ds is a perpendicular surface area in x direction. So velocity in x direction multiplied by perpendicular surface area. This will give me volumetric flow rate. C is the total concentration, kilomole or mole per meter cube, and multiplied by this is meter cube per second. So this will give me a molar flow rate. What this will give me? Moles flowing in x direction. Moles of total moles flowing in x direction. This is a molar flux per unit area. This is total moles flowing in x direction per unit time per unit area. So this will be a molar flux in x direction. What is this Ca? Again, we can have some relation between Ca and C. Most importantly, you know that this will be associated with a mole fraction. Okay, Ca and C, there is a relation between this is mole fraction. You can use it if mole fraction is known. So this C, and you can get the relation between Ca and C. So mole fraction. So Ca into Vx is a molar flux of component A in x direction, and Ca into V is a molar flux of A in a given direction. So this is the convective transport. This is convective transport, and this I think almost we are studying this from last say 10-20 classes. So most importantly, whenever there is a convection, velocity will be associated with that. Velocity, and this is quantity per unit volume. So you can see this is quantity per unit volume, and this is velocity. So you can have different nomenclature based on velocity, which velocity we are getting, which component we are discussing. So based on that, you will get this flux, molar flux, or this is mass flux. Anybody has anything to discuss over this? Any confusion over this? Okay. So with this, we'll have now total flux. We'll always use this combined mass flux. So we'll always use combined mass flux because there is no mass transfer possible without bulk motion, and bulk motion is characterized by the velocity. Now, based on this magnitude of velocity, if this is very, very small, so we can neglect this. If velocities are very, very small, so we can neglect this. So it will be dominated by molecular flux. If this is very, very large, then we can neglect this. This will be dominated by convective flux. So this is the combined mass flux. So this will be a molecular mass flux plus convective mass flux in molar form. And this is say constant density system. Constant density system again in mass form. This is in mass form. This is the molecular transport, and this is the convective transport. This is in molar form. This is in molar form. So this will be a molecular transport, and this will be a convective transport. Again, if total concentration is constant, so this will be a molecular transport of mass transfer, and this will be a convective transport of mass transfer. See, when say now this has some relation with this Na. So, and this you have studied so in detail actually. So you might have started your mass transfer with this equation actually. So with this equation initially you have started, then convection is added, and then convection also then redefined actually. So if I have binary system means a composition in total composition of my compound, there are two components in that binary system. My system consists of two components. Okay, so Ca into V. So how Ca is defined? How Ca is related with the total concentration? Ca is related with the Xa into C. Total concentration into mole fraction will be a Xa into C will be a Ca, and this is a velocity. A velocity can be related with a component velocity. This is not a vector addition. This is a binary system. I have velocity A and velocity B. So characteristic velocity you can think of. Okay, characteristic velocity. So now you can imagine you are defining this velocity of air, and this is velocity of oxygen, and this is velocity of nitrogen. Now somehow you can have some properties of velocity can be used, that using this velocity of oxygen and velocity of nitrogen, I can get the velocity of total air. So characteristic velocity. So this velocity can be split into two parts for binary system, two component system. It will be VA plus VB. Now I can rewrite this equation. Rewriting this equation actually, this will be XA, Ca into VA plus Ca into VB. And what is this Ca into VA? This is again Na. Okay, total flux of A. Okay, total flux of component A. This is total flux of component A. This is total flux of component B. That will be equals to Na plus Nb. So this is also convective flux. Okay, this is also convective flux, and this is also convective flux. Here, most importantly, you need to remember this is not the vector addition of the velocity. This is some characteristic velocity we will be defining based on our system, component property, everything should be involved, so that there will be appropriate relation between this total velocity and individual component of the velocity. This is well defined actually. This is well defined. So individual concentration can be correlated with the total concentration using mole fraction. Rearranging this equation Ca into Va is nothing. Again, this will be total flux of component A. Total flux of component A. This is total flux of component B. Okay, this is total flux of component B. So this will be equals to Na plus Nb. So Ca into B is a convective flux. This is also convective flux. So for binary system, so we'll write Na will be equals to minus C, or total concentration of the system remains constant. If total concentration of the system remains constant, this is true for total concentration is constant. That will be DAB dxa by dx plus xa Na plus Nb for binary system. For generalized system, we'll be using this. For generalized system, this is the equation. For binary system, we'll be using this. Similarly, in mass form also, for generalized, we will be using this equation for mass flux, and this will be equation for binary system mass flux. This will be molar flux, this will be mass flux. So with this information, we can move on in shell balance. So what is the next step? Next step is that discussing the boundary condition to solve the problem. What kind of boundary condition we may encounter while solving this shell balance for mass transfer. Any difficulty in this combined mass flux or molar flux? Okay, so shell balance for mass transfer. Next is, okay, overall equation. First of all, we will discuss. So it is very easy. Rate of mass coming in minus rate of mass going out plus generation minus consumption. Okay, production of mass by homogeneous reaction or consumption. Okay, generation minus consumption you can write here. That will be equals to 0. This will be overall shell balance for mass transfer. This is equals to 0 for roll number 76, Atharva.
Yes, sir.
So when this will be non-zero?
Hello.
When this will be non-zero?
The accumulation.
Yeah, very good. So here we are dealing with a steady state problem only. As soon as we will go in accumulation, this term will be non-zero, and here we'll get accumulation. So in minus out plus generation minus consumption equals to accumulation will be the overall balance equation. In minus out, okay, plus generation minus consumption equals to accumulation. Because here we are dealing with a steady state problems only, hence 0 is there. So, and then to solve this problem, exactly same strategy will be there. So initially we'll use a coordinate system, and then variation of concentration. What are the in which direction concentration will vary? Expected variation of concentration. Then we'll take a differential shell, take a mass balance equation, then use the definition of differential equation. You will get a differential equation. Then substitute the definition of flux. Substitute the definition of flux. Now using combined flux, as we have discussed just now, and then integrate this equation and solve this equation with the appropriate boundary condition. So in this boundary condition, there will be a exactly similar. Okay, a concentration at the surface can be specified. Okay, so concentration at any surface can be given. This is as good as a no slip boundary condition in momentum transfer, and temperature is given at the surface. Exactly same thing is there if concentration is given. Say at XA will be given at say some surface XA0 or anywhere. Okay, XA mole fraction will be given, or Ca will be given. Ca, it is as good as XA. So XA will be given at a surface. Okay, this is first type of boundary condition. Then mass flux can be given. Okay, so mass flux will be specified. So this is as good as you can say uh, air air liquid boundary condition in momentum transfer. In heat transfer, mass heat flux will be given. So it's here in mass transfer, sometimes flux will be given at the surface. That can be used to solve the problem. If diffusion is occurring in solid, okay, now you can visualize what might be the equation. If diffusion is occurring in a solid, it may happen that solid surface substance A is lost to the surrounding stream according to the relation. Which relation is that one? So what is you are expecting after reading this equation? Which equation will come? Roll number 77, Tejas.
And not equal to
Yeah. What, Tejas? Not able to hear you properly. Okay. So this is similar to Newton's law of cooling in heat transfer, and here it is a Slattery equation. What is this equation? Is Slattery equation. So this is if from surface to a flowing stream, the flux can be calculated by using Slattery equation and mass transfer coefficient. This is mass transfer coefficient. So from the surface to a flowing stream. Okay, so mass transfer coefficient using mass transfer coefficient. This is the you can say Newton's law of mass transfer. Na0 is a molar flux, Ca0 is surface concentration, and Kc. And lastly, sometime you need to use a logical boundary conditions also. And sometime here now, as we are discussing mass transfer, mass can be generated and consumed by the reaction also. If there is a reaction occurring at the surface, then so we can have a flux according to given reaction. This is example is given first order chemical reaction. So it can be anything. So if reaction is given, so based on that reaction, we can estimate the flux at the surface where chemical reaction is happening. So there also this is actually you can say this is modified boundary condition of this type. Flux is given, and when the reaction is there, so this flux will be associated with a reaction. This is first order reaction. This is not exactly kinetic constant. This is kinetic constant, and here this is actually not rate. This is flux. According to this, you will get a this is you can say modified rate constant. Modified rate constant, which is relating a concentration with a flux. So that is another boundary condition, and one boundary condition will be there whenever it is needed is a logical boundary condition. So with this information, so we can try to solve the problem actually in mass transfer, cell balance for mass transfer. Now take down this problem. So take down this problem, read the problem carefully, and use all the fundamental which we have discussed in momentum transfer, mass transfer, everywhere, and just see whether you are having enough data to get the concentration profile and everything. Okay. So read the problem carefully and try to solve it. Okay. Try to first of all get the information. So we'll be solving this. So read the problem carefully and get all the information in the data. Roll number 49 Jayant, BT 18 CME, roll number 49 Jayant. Jayant, roll number 70 Darshan, BT 18.
Yes, sir.
Okay. Can you just discuss the problem, given problem? Just ask Jayant to meet me actually. Jayant, roll number 49 Jayant, meet me as soon as possible. Whenever you are getting a time, come and meet me in a department. Hi Jayant, can you discuss the problem? Darshan.
Yes, sir. Sir, here the liquid A is evaporating into gas B,
Okay.
and and the liquid height, it is maintained at Z1,
Okay.
and a gas mixture of AB, both like flows over the surface uh, of the tube, like top of the tube,
Okay.
and it has a concentration of XA2.
Okay.
And sir, at the top of the tube, uh, the mole fraction of A, the concentration of A is XA2, which is maintained there.
Okay. Okay. So this concentration of gas stream is constant. Okay. Even though liquid is evaporating continuously from here, so it is not changing the concentration of A as there is a continuous flow of this gas stream. Okay. The concentration, this gas stream is flowing, it contains A and B. Gas stream is having A and B. Here also we have pure A. Here also we have pure A, and this gas stream is having A and B. So certainly this concentration here is not changing by evaporation rate of this, because there is a continuous flow of this gas stream. So it is maintained at XA2. Then next, Darshan.
Yes, sir. The temperature and pressure is constant in the entire system,
Very good.
and both the gases A and B are assumed to be ideal, like no reaction and all. Uh,
Yeah, point.
Then next,
and also the solubility of gas B in liquid is negligible. Uh, so we have to derive the concentration profile and average concentration for both the gases,
okay. So what
and
is the
also
first
the
step to
flux.
solve the problem?
Sir, first of all, we will get the shell balance equation.
Okay. But for shell balance equation, we need to discuss the input given in a problem, na?
Yes, sir. So we will see in which direction the concentration is changing.
So for deciding direction also we need to fix the what we need to
Origin.
fix? Origin and coordinate system.
Yes, sir.
So what kind of coordinate system
So
is
we will be using Cartesian cylindrical coordinate system.
so this is a type of cylinder actually. You can think of a cylinder. Okay. This is the type
Yes.
of cylinder. In cylindrical jar, a liquid A is filled. Okay, liquid A is filled. It is evaporating continuously in this gas stream. So which coordinate system you will be using?
Cylindrical.
Cylindrical coordinate system. So what are the three directions in cylindrical coordinate system?
So R, Z, and theta.
Okay, so whether concentration is varying in R direction,
Uh, concentration is not varying in R direction.
why?
So,
Because radially the concentration of liquid A remains constant. There is no change in concentration. If you move here to here, concentration is constant. If you move here to here, concentration is constant. If you move here to here, concentration is constant. Concentration is constant in R direction. Hence, there is no flux in or the concentration is not changing in R direction. So there is no driving force as such to change the concentration in R direction. What about theta, Darshan?
Sir, not in theta direction because of symmetry.
Very good. Problem is symmetric around theta direction, so there is no variation in theta direction. Whether it will vary in z direction?
Yes, sir.
Yeah, because here concentration is XA2, and what will be concentration here at this surface, gas liquid interface? What will be the concentration? How to get the concentration, Darshan?
Sir, by Fick's law.
Not fixed law. It's Raoult's law actually, modified Raoult's law. P saturated divided by RT. We have used so many times. If it is liquid and gas, at gas liquid interface, we can estimate the concentration using the equation if saturated pressure is given. Okay, saturated pressure at a given temperature of this liquid is given. So using that, P saturated divided by RT will be the concentration. So here I can estimate the concentration. What will be the concentration of liquid A in this gas liquid interface? So say that is actually you can take it as a XA1, and here XA2 is given. This concentration will be smaller than this concentration certainly. So this will be the highest. So this saturated pressure itself I am using, hence I am saying that this first layer of gas is saturated with liquid A. So that is the maximum possible concentration of A possible in this gas stream, maximum possible concentration. So certainly the concentration of A in this gas stream will be lower as compared to this concentration at this interface. So there will be mass transport only in Z direction. Okay, mass transfer will be only in Z direction, and variation of concentration will be only in Z direction. Concentration will vary only in Z direction. Darshan?
Yes, sir.
So what is expected concentration profile? Now, before solving itself, you should expect the concentration profile. How concentration will change?
Sir, starting from Z1, as we go to Z2, the concentration will decrease.
Very good. Concentration of A will decrease. And
Yes,
as
sir.
this is a binary system, as I am moving from Z1 to Z2, concentration of B will increase. Decrease. No, B will increase. Okay. This is what expected concentration profile. So total mole fraction is 1. This is A. A will be highest. A will be highest here, and A will be lowest here actually. A will be lowest here, and A will be highest here actually. This is B. B will be lowest here, and B will be highest here actually. Okay. So this is how the concentration of A will change. So this is XA. This is XA and this is XB. So don't use this cell for this scale for XA. This is XA. So XA is, say here 80% XA, and here it will be 90% XA. This is the scale for XA. This is the scale for XA. The concentration of A is decreasing. This is say 80%. Not this is 80%. This is say 20%. Then this will be a 10%. This is A is 0. Say this is 20%. So here it will be 10%. XA. So here say XA is 0. This is 0.2. XA1 is 0.2. So XA2 will be 0.1. Concentration of A is decreasing, and this is concentration of B, and this is the scale for concentration of B. So say here concentration of B was say 0.8. This is 0.8, and here it will be 0.9. So summation of this will be a 1. So see this is 0.8 plus 0.21. Here 0.9 plus 0.1 is 1. So this is what expected concentration profile. Expected concentration profile, and why there is no flux of B, because there is a concentration difference of B also. Here I will have B highest, and here I will have B lowest. So in this figure, the concentration of B here will be lowest, and concentration of A, B will be highest here, and B will be lowest here. Why B is not moving in this direction? There is no flux of B. Why? Whether there is a flux of B also? Roll number 4, Aditya. Roll number 4, Aditya. Roll number 1, Abhinav.
Yes, sir.
Yeah. So B having the highest concentration here and B having a lowest concentration here, still there is no flux of B in this direction. Why? Because it is given. It is given solubility of gas B in liquid A is negligible. So initially B will move here and this concentration profile is set. But after this, there is no moment of B. So certainly if B is not moving, so how, so at for steady state problem, so A cannot come in here if B is not soluble in this A actually. Okay, if solubility of B is negligible, B will be here initially this. While in case of A, what is happening here? Concentration is highest, here concentration is lowest. Hence, A is moving in here and continuously it is taken away by this gas stream. Hence continuously this A is moving in this direction. A is continuously moving in this direction. And here that is one assumption we are taking based on solubility of gas B in A is negligible. Secondly, we are assuming that there is no change in level Z1. Even though liquid is evaporating, so there is some mechanism is there so that we are continuously supplying liquid also to maintain this interface at Z1 only. So this is continuously evaporation means it will, this level will come down actually, but we are supplying the liquid also, so this will be there. So what will be the dimensions of differential shell? Roll number 4, Aditya. Roll number 4, Aditya.
So differential shell would have delta Z thickness.
Delta Z thickness. Why you did not responded just a couple of minutes back?
Sir, I have network problems here. My SIM card doesn't work, so that's
What will
why
be the
I have to.
dimensions of volume of a differential shell?
Sir, delta Z because the variation is in Z direction.
Okay. So what is the volume of a differential shell?
So volume would be delta Z into the cross
Surface
section
area.
area of that
Okay.
cylinder.
So this is what this is the given problem. So this will be my differential shell. So this will be flux and NB will be equal to 0. Okay, NB will be equal to 0 because solubility of B in A is negligible. So this is the differential shell. So this is the differential shell cross sectional area into this delta Z, and this is the flux. Flux multiplied by cross sectional area. Flux multiplied by cross sectional area will give me a rate of mass coming in, rate of mass going out. There is no reaction happening in this. Okay, there is no reaction, that will be equal to 0. Overall shell balance equation, rate of mass coming in, rate of mass going out, this will be equal to 0. So this will be equal to 0. So this input, how to get rate of mass coming in, Aditya? Roll number 5, Aditya. Okay, roll number 4, tell me. Flux multiplied by surface area.
Yes, sir. Surface area.
Flux multiplied by surface area. Say S is the surface area. So even though it has a R, it will be total surface area, and this is an AZ. We are discussing flux in Z direction. This is estimated at Z, and this is minus surface area multiplied by this flux estimated at Z plus delta Z. Okay. Now rearranging the equation. What rearrangement you want to make? Roll number 5, Aditya. Roll number 5.
Yes, sir.
So I want a differential equation with respect to Z.
Sir, we'll divide by the constant values.
So constant value and delta Z multiplied
Yes,
by
sir.
minus 1 and use the definition of differentiation. So what differential equation? So here S is a cross sectional area, divide by volume S into delta Z, and taking delta Z tends to 0. What differential equation you will get? Rule number 5. D by dz of NaZ that equals to 0. D by dz of NaZ that equals to 0 minus. Either you write a minus or plus, doesn't matter, because here it is 0. D by dz of NaZ equals to 0. Everybody is getting this equation? Yeah, Aditya?
Yes, sir.
So no difficulty. Now how to get this NaZ? Now if you remember momentum transfer, what we have done at this stage? After getting this differential equation of flux, what we have done after this, Aditya? In momentum transfer?
So we can use the flux formula.
Yeah, flux formula. What is that? Flux formula in momentum transfer?
So Na is equal to concentration into negative concentration to diffusivity into dou XA by dou X
No.
plus
I am
XA.
asking what we have done in momentum transfer. In momentum transfer, which equation we have used? Which is the equation which is relating flux with the velocity in momentum transfer?
Newton's law of
Newton's
viscosity.
law of viscosity. In heat transfer, which equation we have used?
Hicks law.
Hicks law. Here we will be using not Fourier law, it will be combined flux. All the time
Yes,
we'll
sir.
be using combined flux actually. Okay, we'll be using combined flux. So this is for binary system. Na equals to, this will be, and you can add Z everywhere. NaZ, NBZ, everywhere it will be Z. Concentration in Z direction. For binary, and here for this system, okay, and this is you can for total, this is for Z in Z direction. And for this system, NBZ equals to 0. There is no flux of B in Z direction because a solubility of B in A is negligible. So this can be rewrite like this. And now I can rearrange this equation. Keeping this side and rearranging. So NaZ will be equals to minus C DAB 1 upon XA dXA by dZ. Okay. This is for binary system and NBZ equals to 0. Roll number 6, Aksh. Roll number 6, Aksh. Roll number 8, Ali.
Yes, sir.
So did you got this equation?
Sir, I'm getting
Ali,
it.
you are
Yes, sir.
getting. Why NBZ is equals to 0?
Yes, sir.
Why
Sir, it is
NBZ
given,
equals
sir.
to 0? Why it is
Sir, it
equals
is
to
given
0?
the problem. The solubility of B is negligible in A.
Okay. Hence NBZ equals to 0. Okay. And rearranging the
Yes, sir.
equation, you will be getting this equation. Now substituting this
Yes.
definition of NaZ. Substituting this definition of NaZ and integrating the equation. Now integrate this equation twice and use the two boundary condition. Integrate this equation twice and use two boundary condition. You will be getting a concentration profile. Very simple. What are the two boundary conditions available with you? Whether two boundary conditions are available with you? Your roll number 9, Nitin.
Hello, sir.
So now this is second order differential equation with respect to XA. So I need a two boundary condition. Whether two boundary conditions are given in a problem?
Yes, sir.
So what are these two boundary conditions?
Sir, at z equals to z1, xa equals to x1, and z equals to z2, xa equals to x2.
Yeah, XA2. XA2 is given and XA1 can be estimated by using saturated pressure and temperature. All these parameters based on parameters. So you can calculate that. So that XA1 can be calculated, XA2 is given. So based on that, we can solve the problem actually. So that's so this is rearranging this equation as this is the constant. Total concentration of the system is constant. DAB is constant. So this can be taken out. That will be equals to 0. So now this is integrating this equation. So this is integrating first integration, and then second integration will be a minus ln 1 minus xs c1 z by c2. And now certainly this c1 and c2 can be estimated by using a two boundary condition, but as here we have logarithmic term, so we can use appropriate value of c1 and c2 so that it will simplify the equation mathematically. Because this logarithmic term, getting the value of c1 and c2 in terms of logarithmic term will be difficult. So we can assume some value of c1 and c2 logarithmic value, constant only, but logarithmic constant, so that it can be easily estimated using this. For that, so assuming c1 equals to minus ln k1 and c2 equals to minus ln k2. K1 and K2 are also constant, so ln K1 and ln K2 will also be constant. Why this is done? Just to eliminate this logarithmic term in the equation, logarithmic calculation in the equation, so that you can have unique solution to get the unique solution. So substituting this, actually what you will get 1 minus xa equals to K1 square, K1 not square, this is K1 raised to Z. This is K1 raised to Z and K2. Now here I can use a boundary condition. What are the boundary conditions available? So these are the boundary conditions available at z equals to z1, z equals to z1, xa equals to xa1, at z equals to z2, xa equals to x2. So now substitute this in this equation, so and get the value of c1 and c2, k1 and k2, and accordingly you can get the value of c1 and c2. What is the value of k1 and k2? So k1 will be 1 minus xa2 divided by 1 minus xa1 raised to 1 upon z2 minus z1. This is the value of k1. K2 will be 1 minus xa1 whole bracket 1 minus xa2 divided by 1 minus xa1 raised to minus z1 divided by z2 minus z1. So substituting these two boundary conditions, so you should be getting this boundary condition, this K1 and K2. Here roll number 10, Aman.
Yes, sir.
Are you getting this K1 and K2?
Yes, sir.
Anybody else got this K1 and K2 can write in chat box. All people getting this value of K1 and K2 can write in chat box. All people getting the value of K1 and K2 can write in chat box, yes or no. And this, we have introduced K1 and K2 just to eliminate this logarithmic term. Actually, here logarithmic manipulation will be difficult to get the, so to get the unique solution, because this will be non-linear equation. To convert that into simplified equation, so this is the manipulation. With constant we are doing. Okay, constant is replaced by constant. This is also constant, some constant. This K1 and K2. Now here substituting this equation, so we will get a concentration profile. So this is the concentration profile. So 1 minus xa divided by 1 minus xa1. xa1 is given, xa2 is given, xa1 is given, z1 is given, z2 is given. So this is the variation of xa with respect to z. What is this equation? This equation is telling me a variation of z with respect to xa, or xa with respect to z. Variation, how concentration of A changing with respect to z. All other are constant. Z1 is constant, Z2 is constant, xa2 is constant, xa1 is constant. So this is the concentration profile. And how to get a flux profile? So this now this is 1 minus xa equals to xb. This is binary system, because binary system. So you can write this simplified form of same equation. Okay, simplified form of same equation. So this will be xb divided by xb1. This is xb2 divided by xb1, z divided by z1, z2 by z1. So how to get a flux of A? Flux of A NaZ. So I know NaZ will be equals to minus C D AB dxa by dj, and this is equals to, you can say this can be written like this, and this, if you remember this equals to C1. Okay, this whole bracket is equals to C1, and this equals to ln K1. Okay, now K1 is this, so this will be exponential of this will be C1. So you can write this is what NaZ. Okay, so this is K1. So ln K1 equals to C1. So ln K1, substituting this ln K1 minus ln K1 here actually. So you can substitute it here and get the flux profile. So this will be the flux profile. C dAB Z2 by Z1 ln 1 minus XA divided by 1 minus XA1. So this ln K1 and this you know that ln X raised to A will be equals to A ln X. Substitute it here and you will be getting, this will be the flux profile. So everybody is getting this flux profile. Roll number 12, Anand.
Yes, sir.
Did you get this flux profile?
Yes, sir.
Can you show me that flux profile? You are derived.
Hello, sir.
Huh?
Am I video?
I'm not able to see your video.
Hello, sir.
Okay, did you got the flux profile?
Yes, sir.
Okay. Everybody is getting flux profile, you can write in chat box. All the people who are getting this flux profile can write in a chat box. All the people getting flux profile can write in a chat box. So there are only 5 people who got the concentration profile. Okay, so we'll stop here only with this concentration profile and flux profile. So we'll discuss further same problem in next class actually.